Hello and welcome to the Rubber Duck Dev Show. Tonight
Yahoo!
is what, August 11th? Is that right?
Yep. I have to
2021.
check my computer, but yes.
And we are going to be talking about performance. We got a three episode series that we're going to be talking about performance. Tonight we're talking about database performance. Next week we are going to be talking about code performance. And then the week after that is server performance. So we're going to have lots of fun in this series, I'm sure. I am Chris.
I'm Creston.
And we are going to kick it off with some database arguments. Woohoo! Love those. Before we do, just want to let you know, all the viewers out there, you are free to pipe up in the chat. We will participate with you. You can participate with us, argue with us. Tell us how beautiful we are, whatever you want to do in the chat.
Or how wrong we are.
Yeah, feel free. Anyway, so we're going to start out with just a little bit of discussion on some different databases and how performance differs between them. So first, I want to talk about the two big... two of the three big RDBs, the relational databases. The three big ones are Postgres, MySQL, and MSSQL.
There's also something called Oracle.
Well, yeah, but yeah. Anywho, those are the three that you mainly see in the wild. Now, in the world of Ruby, you're only really going to see Postgres and MySQL from an RDB standpoint.
There are people that rock Ruby on Windows.
Yes, there are. And there just aren't that many of them.
True.
And even then, MSSQL isn't always their choice.
Sure.
And there's reasons for that. I'm not saying, listen, all you .NET Windows people out there, I'm not saying that MSSQL is bad. I used it for many, many years. Just not my personal favorite. Anywho, what I want to talk about is the performance difference between Postgres and MySQL. And the reason I want to talk about these is because the differences in them point out some general things to look for in performances with data RDBs in general. First off, the most widely used database right now is Postgres, between the two, by a pretty good margin. That wasn't the case 10 years ago. It is the case now.
Now, are you talking, do you have some metrics that you're pulling this from, or you're saying amongst Ruby on Rails developers? Or
no, there were actual metrics that I looked, and I forgot to link them, but there were metrics that said essentially that Postgres has a bigger market share than MySQL now. Which is, academic, I suppose. Really, what it boils down to is what each of these things is optimized for. Postgres actually works faster with very large data sets than MySQL. And it's better at doing multiple writes, inserts, updates, that kind of thing. It's not as optimized for reads. So MySQL actually does database reads better, more performant than Postgres does in a general sense. Now, again, we're going to have to talk in generalities here because there's huge differences in performance based on how big your data is, what the specific function is, all that kind of stuff. So there are cases where MySQL is going to blow Postgres out of the water and vice versa. In general, in most environments and most applications that I run into, Postgres is either a clear winner on performance or has an edge over MySQL. Because most of the time when I'm dealing with something, the data is fairly large and it's lots of people writing into it simultaneously. So Postgres is optimized for that.
yeah, all I know is I haven't assessed them or did an evaluation. I did an evaluation approximately 12, 14 years ago, and was going to choose either MySQL or Postgres. And based upon the feature set and what was available, I said, okay, I'm going to go Postgres. So I chose that at the time. So I haven't actually examined or done any assessment about which is faster or not, because I've just focused on Postgres.
Yeah, I'm actually working on a project right now that's using MySQL, and it's large data. And I, as much as I would love to convert that to Postgres, that's just not
in the cards.
Yeah, it's not going to happen for a while, if it happens ever, because it's a big deal to migrate databases. It's not a simple thing. As much as we would like to say, hey, just edit the YAML file, the DB YAML file, it's not that simple. There's all kinds of things that go on, because SQL, while structured query language is fairly standardized, there are differences between the different databases, what they implement in their particular SQLs, syntaxes and stuff like that. So the more specific SQLs you've got in your code, rather than something like Active Record that wraps it all up for you, the harder time you're going to have switching from one database to another.
Yeah, I mean, I'm sure they're implementing functions or stored procedures or that differently, or triggers. So if you're using any of those database specific features, and even indexes, there's a lot of different indexes for different use cases in Postgres. And I'm sure MySQL has something different. So you're going to have to adapt and change it to migrate from one to the other.
Right. So it's a good idea to think about your database layer and what you're going to be doing with it before you start your app. If you do that, it is an important decision to make. If you're going to have big data with lots of writes in it, probably want to go Postgres. If you're going to have a small database with mostly reading and very little data changes, MySQL might be better performant than Postgres. Although, that being said, that leads us into our next kind of comparison. You may actually want to go with a NoSQL if you're not doing a lot of data changing. So, depending on your data structure. So, we're going to talk about the performance comparisons between relational databases and NoSQL databases. And NoSQL are things like Redis and Couch and Azure Cosmos and things like that.
MongoDB.
Right.
And within that, I think there's also a separation between document-oriented databases and key-value databases.
Correct. And even in there, the difference between document and key value, one of those is more performant in certain situations than other ones. It just depends. But as a group, NoSQL databases are typically better for unstructured data that's just kind of lists of key value pairs or something like that, like a cache database, which is what Redis is often used in the Ruby world as a cache backend. So because it's just a series of key value pairs, and it doesn't have to do a lot of organization. If you're looking for something like financial systems or things that need multi-record pulls, tables, graphs, things like that, relational databases are typically faster for that kind of stuff. So that's another important consideration when you're thinking about your database layer is, what am I going to be doing with this? And it is not uncommon for those things to be used together. In Rails, we see that all the time. Postgres is your RDB that's used for your data storage, and Redis is your cache backend, and it also handles things like Sidekick, your external jobs and queuing
more
and
ephemeral.
stuff.
Maybe a way to say less. I mean, caching definitely, but it's kind of like your ephemeral data.
Yeah, right. So it's not uncommon to see those things go hand in hand and be used concurrently for different aspects of the overall ecosystem of your app, because each of them does better things. I would never want to use an RDB for caching. because I mean you can, but it's just not good at that. It's you know. Likewise, I would never want to use a NoSQL database to create a financial app like Quicken or something. They're not good at that. Now there are.
I bet there's some people in the comments are like, oh, but okay, yes, it is.
Yeah. Well, and again, I have to talk in kind of very general terms here because there are specific. There's NoSQL, there's new SQL, there's always things coming along that kind of bridge some of those gaps. So, you know, there's NoSQL databases that have some kind of SQL-like DSL in them now that can do kind of structured query language reads on stuff. They're not.
Yeah, and even the whole schemaless thing, some of them have been incorporating schemas or enforcing schemas now. So they're all kind of adding similar features, and maybe they're eventually arriving at the same place. Whereas Postgres started adding JSON support, so it supports more unstructured data now. So they're adding features that kind of, adding features that kind of get to the same point.
Right.
Maybe
yeah,
years
like
down the road.
Postgres JSON-B files with the right kind of index on them, you know, I've used those to actually, in large systems, to actually store, rather than putting settings for something in individual fields, I'll just have a settings JSON-B column that is that has like 40 different settings in it. And with a gen index on it, you can get to those things just as fast, actually even faster, I think, than individual fields. And it cuts down on, you know, having to, hey, we need to add this feature or this setting to this model. Now we got to change the database. Well, no, you don't. If you're using a JSON-B settings field, you just add it to your settings structure. And so, you know, and that's kind of an emulation of a NoSQL structure. So,
or non-structure as it would be.
Yeah. Because ordering has no bearing on what's in that field. It doesn't matter what order that data comes in. It's just there. And there's no real structure to it other than its key value pairs, and it's JSON, but that's not the same kind of structure that when we talk about relational databases.
Yep.
Anywho, so yeah, the big point of this beginning of the conversation, though, is you really need to think about your database layer when you're designing applications, because that can have a very big effect on how hard it is to scale it, how hard it is to change it, and how fast it can be, how much data it can handle, based on what you're going to be doing with it. So, you know, just think about those things before you start implementing your database. It also has a lot to do with database design. What models are you going to have? It depends. If you're using NoSQL, that's going to be very different than if you're using an RDB. So, all right. So I am going to mostly shut up now and let Creston take you on a whirlwind tour of Postgres specific things to increase performance of Postgres specifically. Now, a lot of these things will apply to other databases. There's some general ideas here that will carry over. But as Creston is our resident database expert, guru, Mr. Man, I'm going to shut up and let him talk to y'all.
Okay. So like I said, about 12 to 14 years ago, I was assessing MySQL versus PostgreSQL, and just based upon the feature set, because I had come from using Microsoft SQL Server, and then I had started using Oracle in my job, and then I was going to choose database, and between MySQL, PostgreSQL, and because probably coming from Oracle, I liked the feature set that PostgreSQL had at the time. So I said, all right, I'm going to choose that and never look back. But I still think it's a great choice. And in terms of the popularity, it continues to grow, and it has a lot of feature sets that still it's building on. And so talking about database performance, I know we're going to be talking about a number of different performance areas, but to my opinion, if you're dealing with large data, or I'll call it large data, not necessarily big data because that implies something astronomical, but if you're working with something large, being able to work with that data fast, improving your database performance can give you more wins than probably anything else. I'll go out on a limb here and say that, because if you have working with a lot of data and you want to upgrade your database, well, you can throw more hardware at the situation. Maybe that could improve your performance by 2 times or 5 times just by increasing the amount of hardware. It would be very hard to do 10 times or higher. You could also try doing tuning of your database system. Again, it could be Postgres or MySQL or whatever, or even Oracle. But again, maybe that just gives you a 2x or a 5x improvement just by that tuning. Now, that's nothing to sneeze at, but it is a small win when what you can do in terms of changing your code. But if you have the right schema design and the right query optimizations of the queries in the database, you can get huge wins. And I'm talking like 1,000 times improvements in performance, or 10,000 times improvement in performance, because I've seen these changes that can happen if you kind of know how to structure your queries.
And I've run into many situations where just adding a missing index to queries that get run a lot of times make huge differences. Yeah. Or optimizing the syntax of a query, doing a union instead of an inner join or an outer join, or doing things like that, depending on which database you're using. But those query optimizations are big, and that's almost always where I start when we have some kind of speed issue we're trying to solve.
Yep. And so with that's kind of where I'm going to try to keep most of the focus is on these types of query wins in terms of using the database. Now, my first piece of advice is to let Postgres do its thing. So what do I mean by that? So I know with a lot of programmers, some of them struggle to the concept of declarative versus imperative, meaning they have a hard time telling the database, hey, just give me this data where it equals this, because that's what a select statement is. Whereas more imperative is you're saying, I'm going to pull the data, I'm going to do a loop, and I'm going to pull the data over one at a time, what I need. So basically what I'm saying is that when you're using the database, use the database, don't try to build around the database, because you can get yourself into a huge problem if you do something like, hey, let me pull this data from the table, and then locally in Ruby, I'm going to filter it, I'm going to sort it. No. Let the database do it. So construct your query to filter the data using a where statement, order it on the database, and then pull back the data to you. Let the database do its thing.
And Rails is very prone to falling into that trap. I see that a lot, where because Active Record it'll create queries for you, but a lot of Rubyists, especially newer ones, get into this habit of just looking at the Ruby call, the Ruby code, and not paying attention to the queries that are developed underneath. And I see more and more like N+1 queries and all kinds of stuff where they're doing loops with 1,000 queries when they could just do one query and be done with it.
Yeah. The other thing that I haven't seen it as prevalent, but it's also a possibility, is excessive use of cursors. So again, that's like pulling data and then pulling over it one at a time. That can, particularly with Oracle, that can get really slow. But I haven't seen it that much with Postgres. But again, that's kind of, again, working around and not letting the database system do its thing. So you want to try to avoid that and actually use properly structured SQL to pull back the data for you. Let it do most of the work. Because the other thing about it is that all of these relational database systems are predominantly built on C. So that is a very performant language compared to Ruby, compared to Python, which are slower to process things. So you're going to get a speed boost just from that using the native, capabilities in your relational database system. So the next area to consider is in terms of indexes. So as a first pass, you basically want to have a primary key on all of your tables. And basically that is an index on whatever your primary key is. It could be a surrogate key, like for example, Rails by default creates a serial, basically an auto incrementing integer for the table when you create it. So that's a good practice. The other, you could also go with natural keys. You define a primary key across existing actual data rows in your table. So you could do either of those methods, just make sure you have defined a primary key for every table. And the other thing is define an index on any foreign keys on that table. So a foreign key is if you're referencing another table, referencing its primary key, like if you are referencing the orders table and you have an order ID and you want to index on that order ID in the table that you're working with. So that's just kind of a baseline you want to make sure you have.
And sweet Lord, make sure your primary key is unique.
Well, yeah, that's the point.
Yeah, you think that everybody would know that, but they don't.
Now you got me thinking. I was like, wait a minute, does Postgres enforce that if you actually say it's a primary key?
I think Postgres does. I think most RDBs do if you call it a primary key.
Yeah.
But if you specifically name it in the database a primary key, however, what I have seen is people say, this is my primary key, but they just put an index on an integer.
No.
And that's not a primary key. So don't do that.
Yes, use a valid primary key. Okay. So the next area that you're going to want to think about, particularly as your database size grows, is what kind of maintenance is necessary to keep your database up to date. Now, I'm not talking about maintenance here per se, but Postgres, for example, has a process it calls vacuum. So how Postgres handles its concurrency control is it uses something called multi-version concurrency control. So what that means is it keeps multiple rows of data as it incorporates changes or deletions so that other people who are using the database system can potentially get a different version, a different view of that data. So for example, when I go and I update a row and I update in a column, say A to B, it actually retains the old row for as long as that version needs to be around based upon who else is connected. Then vacuum comes around and essentially vacuums up or deletes that row so it doesn't exist anymore. So that's the main purpose of vacuum, but vacuum also does other things to help keep your database optimized. So it also does things like update a visibility map, which can be important for certain types of indexes to work efficiently, as well as gen index performance that you were talking about before, which is typically an index you put on JSONB, or if you're doing full text search on text columns, that becomes very important, the frequent vacuuming for that. So basically you want to take a look at your Postgres tables to make sure that they are vacuumed on a regular basis and that you have auto vacuum running. Now it runs by default. And again, if your database is small, you probably don't need to worry too much about this, but as your data size grows, that becomes more important, is vacuuming frequently enough. The other thing that also vacuum handles typically when it runs is doing an analyze. And what that analyze does, it's a separate process, but it works within vacuum, is it analyzes all of your data to collect statistics. So how Postgres works, or the planner works, when you give it a query, the planner looks at what you're asking for, looks at the structure of your table or tables, the indexes that are available, as well as statistics about what values exist within each column. So for example, the statistics of a column that just has, say, 3 values in it will be very different than an unique ID column that has all sorts of different unique values. So those statistics are stored, and they need to be kept up to date so the Postgres planner can understand how to best structure the query to give you the data you need.
And the
So that's
planner,
it.
so let's, you're saying planner just quickly. So you're talking about the thing that decides which indexes should I use, which order should I execute these bits in, that kind of stuff.
Right. Again, because you're just saying select all these orders after this particular date and join it to the warehouses that exist in the US, all your query that you're asking for that information, it's the planner that actually does the intelligence of, okay, I'm going to choose to use this index and this index in this table and do this type of join on them, and then do a filter by this. So it's the planner essentially doing the coding for you.
Mm-hmm.
So someone's developed, you can call it an AI if you want, circa 1980. So it's basically deciding the query that you give it, how am I actually going to execute it? So that's what the planner is. So it needs this statistical information to make the best plan to pull out your data efficiently. So like vacuum, you're going to want to make sure that you're analyzing frequently enough so that your statistics are up to date. Okay, so the next area to talk about is that when you're actually having problems that you want to identify what's going on. So for this, I'm going to take a look at this. So the number one extension, in my opinion, to do this is PG stat statements.
Links
now again,
below.
Pardon me?
Links below.
Yes, links below. So Postgres has this concept of extensions. So you can basically add additional modules to Postgres to give you additional features. And this, in my opinion, is probably the most important one that I always install. And it's called PG stat statements. And it's basically collecting statistics on all statements run against the database. So it's a view that, excuse me, it collects all the inserts, deletes, updates, selects that are run against the system. And it gives you a parameterized view of them. So for example, if you have a table that says select, all from the orders table where the ID is 2, and then you have select all from the orders table where ID equals 5, those are essentially the same query, the same plan will essentially be used. That just shows up once with select all from orders where ID equals like $1. It's basically a parameterized version of the query, and that's what it stores in PG stat statements. Now, I'm sure other databases, I haven't used Oracle or MySQL frequently enough, but I'm sure they have something equivalent that allows you to look at what statements have been run on the database system over time. Now, this gives you information. First, it shows you that parameterized query, so you can look at what query you're talking about, but then it lets you know, was this the right? Okay, so it gives you, let me see if there's a better version of this, because I was looking at, no, okay. So it lets you know total time spent doing planning, total time spent doing execution, how many calls, how often this query was called. Now, to me, one of the most important things I like looking at is the total time spent on the database running the query. And it looks like this, like total execution time. So that tells you how much. So basically you can look at that and you order by it, and it can tell you this statement is taking the most time in your database. And you can say, hey, it's taking up, if you factor in all the number of different statements you're tracking, maybe this query is taking 25% of your database, is spending time running this query. So if you could optimize that, that could give you much better performance of your overall system. So a lot of times I work with clients and we just look at this PG stat statements and we just start knocking out the top queries taking the most time. And then suddenly they don't need to upgrade their database anymore. So for me, this is a huge example of how you find the statements that are taking the most time that you can then optimize. Now, then the question is, okay, this helps you find those queries. How do you optimize them? And that is using the tool in Postgres called Explain. And again, I'm sure other databases have something similar.
Yep.
It basically tells you what plan the planner has decided to execute. So basically, you just have your statement. It could be an insert statement, delete statement, update statement, select statement, and you just put Explain in front of it, and it tells you what plan it intends to do. And a lot of times what I like to do, at least with select statements, is do an explain analyze, because then it exactly runs that query and gives you a report on the timing. So it does show you the plan and then how long it took to execute that plan, each individual component. And it looks a bit like this. So for example, for something very simple where, this is select all from a table where the unique is less than 7,000, it'll tell you, okay, my query plan, I'm going to do a sequential scan on that table. So basically it's going to look at the table and go through every single one. But if you add an index, the plan can change. So now the planner will know, okay, there's an index now. So now I can now do a bitmap index scan on this table. So I don't have to just go through every value of the table. I can just look at an index, and a lot of times you get much better performance. So you can look at the cost estimate goes from 483 in this case to 229 in this case. So it gives you better performance.
And this is a place that I start a lot when I'm investigating long-running queries, because this is one of the easiest ways to find missing indexes. Because if you start seeing a bunch of table scans in your explains, that's when you need to start thinking, well, why isn't it using an index? Either A, I don't have one, or what sometimes is the case is the index is actually slower than just table scan because the data isn't distributed enough. So for instance, like you almost never index Boolean fields because there's not enough distribution of data for the index to be effective. But that can happen in any type of field. If you've got like let's say you have a settings field that only has 3 possible values.
Or a status is what I see a lot.
Yeah.
Like a status only has predefined. And that, that is there's a term for that, cardinality. So there's low cardinality for that particular column.
But
so an index is not going to be as efficient on that.
Right. But going through the explain, when you start seeing table scans, that's where you want to concentrate first and say, okay, am I missing an index, or is this a cardinality issue?
Yeah, and generally what I like to do, because a lot of times the queries got a lot more complex, is that I look through and say, okay, so the total cost of this is 713. And well, is there, I guess I'm looking for something a little bit more complex. So here they did an explain analyze of this, and we'll just look at the timing here. So approximately 7 milliseconds for this whole thing. But then I try to find, okay, what area is taking the most time? This is super fast. That's super fast. Starting to get a little slow here. And here you're doing a sequential scan on the table. So, okay. So like you're saying, all right, so I probably need an index on this table to speed things up.
Right. Now, deciding whether you need a simple index or a compound index, or that's a bigger discussion. There's whole courses on how you pick an index for your structure. But in most cases, if you see those table scans, you likely need an index. That's the most common case. unless it's a
Yeah.
very low cardinality field, like a Boolean or a setting or something.
Yeah, and it looks like they, looking through this example, and I actually didn't look at this in depth, but they've whittled down the performance of this, adding additional things, and now you can see it's doing a bitmap index scan. So apparently they added an index through here, and they got execution, sub 1 millisecond.
Right.
So it's basically you look and see where the bottleneck is in the query plan, and you address it, typically through indexes, or you rethink how you're doing the query or something else. Or again, going back to the statistics, I've seen the case where something's just not working. And if we ramp up the statistics for that table, again, this with larger systems or large amount of data, this gets where some impact can come in. You could get a better query plan out of it.
Yep.
Okay. So now, of course, when you're doing this, the next thing I was going to talk about is index types, because Postgres has a lot of index types. And a lot of probably the examples here are just using single column indexes. But depending upon how you're pulling data, compound indexes can give you a big boost in terms of querying. So if you, like, for example, SaaS apps typically have some sort of a tenant ID or an account ID that's on almost every table. And frequently when you're querying table, assuming you have all the tenants in a single table, you're always going to be using that to pull data. So you're always going to pull by the tenant ID or account ID as well as some other value. Well, having that in a compound index or a composite index, basically a multiple column index, can give you a big performance boost. So that's one thing to consider in terms of addressing your slow queries is, are there instances where I could use a compound index that would give me a more efficient plan? Other types of indexes that you should take into account are partial indexes. And what that is you're only going to index part of the data set. So for example, if you're only, and one area I particularly like partial indexes, exactly what you were saying about a Boolean. So if you have a Boolean field, it's hard to index that. But what you can do is actually create two different partial indexes. So you have one index where that Boolean value is true and another index where that value is false, as long as you're choosing some other column, for example, in the index.
Mm-hmm.
But with that, if you are checking that the Boolean is true, it will use one of those partial indexes. If it's false, it'll use the other index. And that can give you astronomical performance gains
Mm-hmm.
because in addition to Booleans, like things I was talking about, the status fields, if you're checking the status, that's another way I like to use these partials. Now, yeah, you're going to have more than one index on a column, essentially, where the status is A and where the status is B and where the status is C. But Postgres is fine with having multiple indexes, but it can really give you a huge boost to performance because it's no longer it's a smaller index because you're only storing just part of the data, and it doesn't have to scan through that status column. It just chooses the index to use, and it's scanning everything else.
And while we're talking about indexes, let's touch real quick on why would I not just want to throw an index for every field in my column? What's the downside of that?
Well, the downside is for maintenance. So basically, every time you're going to insert data or update data, those indexes have to be updated as well, particularly if the data is going to be impacted. What you're inserting and update is going to be impacted because it's in the index. So you want to be cautious that it's going to diminish your insert, update / delete performance. Like you may get great select performance, but you're going to diminish that type of performance. And you don't want to, that's why I said at the beginning, you want to start with primary key and foreign key.
Mm-hmm.
Your primary key and your foreign keys. And then And then of course, I add a few more based upon how I know I'm going to be querying it. Like, is there an account ID? Should I do this as a multi-column index on the tenant, or the account ID? Or is there a date time I know I'm going to be using frequently? I'm going to change things there. But basically to start, just a primary key and a foreign key.
Right.
Because so many times you're not going to be querying all these other areas, but you could use things like PG stat statements to key you in what queries are taking the longest and what do I need to keep a lookout for.
Right. And it's important to understand how indexes work in your particular RDB, because that's one of the reasons you don't want to typically index low cardinality fields, is not because it's bad to index it from a theoretical standpoint, but because it doesn't help you enough to overcome the loss of performance you get by having to update that index every time you change the record. So understanding how those things works helps you make better decisions about which indexes you should use and when you should use compound versus single indexes and when, that kind of thing. So it's really important to understand indexing strategies in the database if you want speed improvements, because indexes, like I said, when we have a speed issue, when I'm trying to tackle a speed issue, the first thing I do is look for slow queries. And when I find them, the first thing I do in there is look for index problems. And that's usually where I can get 90% of my performance increases.
Yep. So we were talking about partial indexes. The other index, like you were talking about, hey, there's an index here, but it's not using it. I get that a lot from support requests, because, and a lot of times it's because you need an expression index. So in terms of Postgres, if you put in, let's say email, let's say you have a column in a table that has an email, and you have an index on that email. But when you go to query it, you're saying, I'm going to ask for a function of lower of the email. So you just want to do a search through it looking for lowercase emails. Well, the problem is that's now considered an expression index, and it's not going to use that index. So what you actually need to create, if you're going to query this email field that way, like you're always going to be using this lower or lowercase function to query that column, you need to add an index that has that function in it, and then Postgres knows to use it. So you can't just have an index on email. You need to do an expression index on email where you're saying lowercase the email. So that's another index consideration you need to take into account. And you can see that when you do an explain analyze, why is it not using the index? Well, it's because of that. Or I've seen also cases when people are trying to do a search. So particularly a wildcard search where you're just looking for an instance of something within a text field. Indexes aren't going to really help you there. There are certain ways you can do a B tree index such that you can say, look for maybe the first part of it, but trying to find a text string within it, it's not going to work. But then you're looking at different features like full text search and gen indexes. So these are entirely different features of Postgres that'll enable you to index this text and be able to retrieve it very quickly. So that's
gen indexes,
another thing you may run into.
Yeah, gen indexes and full text indexes are a much different animal than just data indexes like we're talking about here. It's almost like they should have named them something besides index, because it's almost a completely different thing other than conceptually it's ordering data and making it searchable.
Well, I mean, there's a lot of different indexes, rum and gist and brin and, that have all their different use cases. So, the main index is just the B tree. So that's mostly what we're talking about. But there are the next one you'll probably hear or use is a gen index, but there's also other index types that have their specific use cases. Like if you're doing geographical information systems, you're going to be using SPGIST or just, but as you get into that, you can, do some more research in that area. And I think we should kind of describe, at least for Postgres, just so people understand that there's the data tables, and that is called the heap. And that's one structure. Indexes are entirely different structures. So they can look and appear differently. So a binary tree looks very different from a gen, but it's kept independent of the heap. And a lot of times when you're querying something, you look up something in the index through this one structure. But then once you have the reference to it, you then consult the heap to pull back all the data for that row. And that's typically what you're going to do in Rails when you say you find account 123. You're going to, presumably that has a primary key. It's going to look through, find ID 123, and then it's going to pull back all the data for that row going to the heap. So that separate structure and pulling that data over. So that's typically how things work. Another area that you can focus on for performance is trying to do index-only scans. So what that means is you're going to do a query you want to query your database, but you don't want to access the heap. So for example, if all you need is an ID from, say, the account table, then Postgres knows, hey, I just need to look in the index. I don't need to then look it up in the heap. So that gives you a more immediate result. You just immediately consult the index and pull back the data. That's called an index-only scan. And what you can do is add additional columns to that index. So if you have, this may bring up the case of where you may want to use a multi-column, like if you're putting account ID and processed at date time, you could have that in your multi-column index. And if all you're asking for is those pieces of data, you can pull them over in index-only scan. And if you're using later versions of Postgres, there's also the include statement. So what that means is you can actually, to your index structure, add additional columns to be able to get more index-only scans. So those columns will be pulled over with your index-only scan.
And that's a huge performance thing, especially I see this a lot in Rails where people just say, give me the entire record. Only select the fields that you're trying to work with. And if you've got something where you're selecting, let's say you've got an endpoint that gets hit 1 million times a day and it uses 4 of 53 fields out of a record, put those 4 records in an index and only select those 4 fields in an index and only select those 4 fields. That massive performance improvements just for thinking about things like that. And
you can, and like, again, like trying to put an index on every field, you don't want to put your whole table in these includes, because then you're not helping. But there's a balance.
Your index becomes the heap.
Exactly. You're doing double time, and then your boss is coming to you, why are we using so much space in the database? So it's a balance, but for certain use cases, they can grant you, huge performance improvements.
Yeah, like if I had a query that was running 20 times a day and it used 5 fields, I wouldn't bother to index those 5 fields. It's not running enough. But if I have one that's running 1 million times a day, that's probably worth an index.
Yeah. And, it just depends on, like I said, just check out, at least in Postgres, check out your PG stat statements and you'll know what is taking the most database time. Or if you know something's particularly slow, you can just use explain to analyze what's going on and figure out how to improve it.
Yep.
So I know we spent a lot of time on indexes, but there's one final area in terms of performance that I do want to cover, and that's kind of changing data. So we've talked a lot about selecting data efficiently and and whatnot. But just wanted to talk a little bit about that. So Postgres is very good at inserts in terms of speed. The primary reason is that there's no locking going on, because whenever you're going to do an update, it requires a lock. And this is true for all relational database systems. So, but also the updates are more harmful with Postgres compared to some other relational database systems due to its multi-version concurrency control. Again, because it keeps those old rows around in the table. So if you have, a one row table, but you update that one row in that table 50 million times a day, you've just generated over that day 50 million rows in that table. So essentially you're probably going to be bloating the table because vacuum can't keep up with the volume of data that's being updated. And again, you're probably going to have logging issues and whatnot. So Postgres does have issues with that. There's other database systems that handle it differently. So they have a separate undo or rollback area. So basically they update that row in place. So that row in the one row table gets updated 50 million times. But those 50 million history transactions are stored in the undo or the redo. So it's hard to do a rollback with these other systems, but they're not going to create the bloat problems that Postgres does. So all that being said, when you're dealing with Postgres particularly and other relational database systems, it's usually more performant to do an insert versus an update. So if you have that case where you need to update something 50 million times, you may want to consider doing those as inserts and then deleting them later, or reach to another data store to do that. Do something in Redis that then updates something in Postgres maybe every hour with what the current value is or something. So it's just something to keep in mind when using your database system, that particularly relational databases, there's a higher penalty for updates and deletes versus just straight up inserts when modifying data.
Yeah, and deletes in most RDBs are pretty expensive operations too.
Yeah.
From performance standpoint. And they also cause some, I won't say issues, but they cause speed, I guess, in the vacuums, because when you delete a record, it's not actually deleted, it's just marked as delete, and then later on the thing has to actually expunge all that mess, and there's just more stuff to do. Also, there's a lot of a funny story about deletes that I run into.
There's always funny stories about deletes after the fact.
Yeah. But I run into this a lot, and this isn't a destruction of important data thing. This is it causes so much confusion in people who are new programmers, because they don't realize that most RDBs just tag something as deleted. And if you start inserting new records, it starts backfilling those slots. So if you do a select statement with no ordering, you'll start seeing records in all kinds of weird orders. And they're like, well, wait a minute, I just inserted these. What are they doing way up here? Well, it's because it just reused one of those delete slots. And they don't understand how that works in a database, really. They think delete means just get rid of it and then start adding stuff to the bottom. But and it's just funny because I see that a lot when I'm talking to newer programmers that haven't run into, they're just starting to get into databases and stuff. And they're like, what is going on here? These should be at the bottom. No, that's not how DBs work.
Yeah.
So
that's what they made the order clause for.
Right. That's why you have to do that. Never, one of the cardinal rules that I see broken a lot is never assume order in a database, you have to specifically tell it, I want the records in this order. Otherwise, you can't count on any order in a database.
Yep.
Ever. So if you're doing reporting and you're running queries that don't have an order statement, you're doing it wrong. You just are. And it's going to bite you at some point.
Well, the worst delete stories are executing a delete statement without a where clause.
Oh, God, yeah. Fortunately, I've only ever done that with staging data, never production data, but it can easily happen.
Yeah.
I've been lucky. I'm also extraordinarily careful with delete statements because...
Well, I always select exactly what I'm going to do, and then I delete the select and put delete. So there's always a where at the end.
Yeah. So...
But an even safer way to do it is to use some program. Like I know people that, oh, I never access the database terminal. I always use Ruby to do my query because they don't want to accidentally do something that blows away their data.
Yeah. And with deletes, that's not a bad idea. With the other stuff,
yeah.
But
yeah. Well, as long as you're only doing selects, you're not gonna.
Well, even inserts and updates, when you're doing batches of stuff, a lot of times it's much faster to batch up one query because you can do batch inserts and updates in the query itself and just send one payload and let the database take care of it. So, and that's another thing to be cognizant of with databases is every time you make a query call, every query you call has to go across the wire. So you've got, package
latency.
There. Yeah. It has to, the database server itself has to get hold of that query, parse it apart, figure out what it's going to do with it, with its planner, and then execute it, and then turn around and send it back to you. So the less times you can do that round trip, the much faster you're going to be, which is why N+1 queries are such a ball buster in speed issues. Because, I'm going to get the addresses for every person I pulled, but I pull this list of people, and then for every person, I shoot off another query for the address. Well, that's not good. Pull all that stuff at one time, and then do what you got to do. And, pull as little as you need. Don't do select star. You almost never need select star. It's just adding stuff to what's got to come over the wire.
Yeah, and then you're bloating your application processes too, because they're taking all that data and they don't need it.
Right. Yeah, because every Ruby object that's got to be instantiated with all that stuff, it much quicker to instantiate an object with 5 fields than 50. Especially if they're a bunch of string fields. Those are expensive. So, PSA, boys and girls. Be cognizant of how many queries you're sending. But I think, for me, one of the biggest things with databases is understanding how indexes impact the database and how they impact query performance. So, I think understanding indexes in your RDB that you're working in is extraordinarily important. You should understand how they work, not just that they exist, but how they work. When it's good to use them, when it's good not to, when it's good to use multi-indexes, when you don't, because there are cases where I may be querying by, multiple fields, but I don't want a multiple index for that. I want them in separate indexes because that's actually faster sometimes. But understanding when that is a big part of getting speedy databases. Anywho.
Yeah, if you're looking for that 10,000-fold improvement, knowing your indexes is a good step towards doing that.
Yeah, getting the stats to find your slow queries, knowing how to read and explain so you can understand that particular query and what its problems are, and then knowing when and where to apply indexes is how you're going to get huge performance improvements real fast and get big raises because your boss is going to think you're Superman. So anyway, hope you guys enjoyed that. This has been the Rubber Duck Dev Show. I'm Chris.
I'm Creston.
We're here every Wednesday at 8 o'clock Eastern Time. Next week, we're going to be talking about code performance. Number 2 in our 3 series, our three, what am I saying?
3 show episodes, whatever. 3 episode show?
Okay,
No,
you don't know
I
either. 3 episode series? The programmers, y'all, give us a break. Come on. Anyway, if you enjoyed that, please like, subscribe, comment, smash all the buttons and ding all the bells. You know the deal. If you're looking for, if you're watching this on YouTube, we've got a lot of good links down below. If you're watching this on Twitch, go look for it in YouTube where the links are.
No, or go to the website, the Rubber Duck Dev Show.
Right, rubberduckdevshow.com has all the links with each video as well. Also, we just got so much stuff going on, I can't keep track of it. But anyway, we'll be back next Wednesday, 8 o'clock on Twitch and YouTube with more fun. Make sure you bring your friends, bring your kids, bring your grandparents. We don't care who you bring, just bring somebody. And until next time, happy programming.
Bye.
Bye.